Number 1, cyclopentene. Great. We don't need to say that it's cyclopent-1-ene or 1-cyclopentene, because where else would it be? Here, we've got 1-methyl. And again, we can also call this cyclopentene, because where else would the alkene be but on the first carbon of the ring? You can also call it 1-methyl 1-cyclopentene or 1-methyl cyclopent-1-ene, just to reiterate that the alkene is on the first carbon. Yes, I know in the last class there were some people that named this as 2-methyl, counting through the alkene clockwise. But that means you've got two options, 2-methyl cyclopentene or 1-methyl cyclopentene. So you're going to choose the total lowest locant set. Here we don't have that choice. Again, we could say 3-ethyl cyclohexene. Well, we could if I could spell it. But saying 1-cyclohexene is not bad. Oh, but that doesn't say hexene, does it? There we go. It said pent, but it was a 6-membered ring. Small little typo in this one, which is 5-bromo cyclo-1,3-hexadiene. You can also call that 5-bromo cyclohexa-1,3-diene. Remember when we learned about nomenclature, we said that those locants can go prior to the suffix or inside right before the suffix. I'm sorry. They can go prior to the root or inside just prior to the suffix. I know on Monday, a number of people named this as 6-bromo cyclohexa-1,3-diene, just numbering the other direction. Again, the diene gets the same locant set, so now you're just minimizing the locant set for the bromine, similar to the methyl group up here. Common error, I want to take a step back. Common error I see with a compound like this is trying to get the ethyl on carbon 2. So they'll number from this carbon of the alkene and around, but we're not allowed to do that. We have to count through the 2 carbons of the alkene. Small typo here. We don't list where the diene is. To be fair, based on the name, there's really one best way for the alkene to be listed. But IUPAC tries to be all about redundancy. 3,3-dimethyl, 6-isopropyl, 1,4-cyclohexadiene. Here it doesn't matter which way you number to get 1,4 for the diene. You could start on any 4 of those carbons, and you could number any direction, you'll always get 1,4-hexadiene, cyclohexadiene. So then we're minimizing the locant set for the 3 other substituents. If I numbered in a direction that heads towards the isopropyl first, I get a locant set of 1 for the alkene, 3 for the isopropyl, 4 for the second alkene, and 6 for the dimethyls. If I number in a direction that goes towards the dimethyls first, I get 1 for the alkene, 3 for the dimethyls, 4 for the alkene, and 6 for the isopropyl. What's the lower set? Yeah, 3 is lower than 4 at that first point of difference. Okay. 3-methyl, 1-butene. Perfect, no notes. Here we've got 2-methyl, 1-propene. Technically, on propene, there's really only one place it could be, so you could call it 2-methyl propene, but yes, you're right. Thank you. I didn't even catch that. Dimethyl is alphabetized by methyl, and isopropyl is alphabetized by I. So this would be 6-isopropyl, 3,3-dimethyl, 1,4-cyclohexadiene. Thank you, Yoon. I don't know if I didn't see who put these up there. Is anybody willing to say, was that just going by the locant set or accidentally alphabetizing by die?
That was me. I just flipped it on the board.
Huh?
I just flipped it on the board.
You think by locant set, you think you just put the lower locant set? But you have it right on your paper? Oh, sad.
I just wrote it out.
Okay. 2-methyl-1-propene, 4-bromo, 2-pentene. There is information we can add to this name. The locant set is correct. I need to minimize the locant set for the alkene. That means starting from the right. But there's information I can add about this alkene. Does this alkene have stereoisomerism? Is this alkene a stereoisomer? What do we look for to decide if an alkene is a stereoisomer or has stereoisomerism? Not if it's chiral, because chiral is all about three-dimensional arrangement in space, and this is actually two-dimensional planar. Both carbons have how many? Have two distinct groups. So I want to talk about some overlap and distinction. Chiral carbons, we said, have 4 distinct groups attached to them. Stereocenter alkenes, which are not chiral, but they are stereocenters, similar to chiral carbons, do they need to have 4 distinct groups? 2 on the first carbon, another distinct 2 on the other carbon? Does this alkene have 4 distinct groups, or are 2 of them hydrogens? 2 of them here are hydrogens. So it's not a total of 4 distinct groups like chiral carbons, but it's 2 sets of 2 distinct groups. Hydrogen versus methyl, hydrogen versus this bromoethyl, if you will. Is this a cis or trans alkene? This is trans. The low priority to high priority, low priority to high priority, they point in opposite directions. Or if you dissect this alkene parallel to the double bond, the low priorities are on opposite sides of that dissection. I like to do the arrows. That's what works best for me, but I have students that like the dissection method a little bit better. So would I give this E or Z? This is E. The high priority groups are on opposite sides. They are not on the same side. 3-chloro, hex 3-ene. Here, it doesn't matter which direction I number from. I get 3-ene from either direction. Since it's a tie, I go to the next lowest priority and I look for the chlorine. So I'm going to number from the left so that they both end up on position 3. But there's information missing. Is this E or Z? What's the high priority on this carbon? The carbon or the chlorine? Chlorine is high priority. What's the high priority on this carbon? Hydrogen or carbon? Carbon. High priorities are on the same side. Remember, you're looking at the highest atomic mass at the first point of difference, not the highest group mass. So you're not adding the mass of ethyl and comparing it to chlorine. You're comparing carbon to chlorine. So this is Z, 3-chloro-3-cyclohexene, or we could call it cis, 3-chloro-3-hexene. Great job. Okay, same thing down below. 3 cyclopentyl, 4 methyl, pent 2-ene. They numbered from the right to the left. They got a 5 carbon chain, pentene. That means cyclopentyl is coming off of 5, methyl is coming off of 4, E or Z. What's the high priority group? Carbon or hydrogen? Oh, not a trick question. Off of this carbon, carbon or hydrogen, which is higher priority? Carbon. Okay, now off of this carbon, what is higher priority? Carbon or carbon? No difference yet. Carbon or carbon? No difference yet. Carbon or hydrogen? Carbon. But remember, with these higher priority things, when they're just alkyl chains, I actually gave a tip back in chirality that we can look at the substitution of the carbon will eventually have more carbons that win out against less carbons. Tertiary versus tertiary, no difference. But secondary versus primary, as I move down the chain, secondary wins. Secondary will have more higher atomic mass groups later on down the chain. So this is high priority. From low to high, my groups are oriented in opposite ways. E. E, 3 cyclopentyl, 4 methyl, pent 2-ene. Here is our R3-chlorobute-1-ene. You could have also drawn this flipped over. Oops. Like this. Or you may have drawn it like this. Highest priority on that chiral carbon is chlorine, and then the alkene carbon, and then the primary carbon. So that's R. R looks S, but is backwards, is R. E2-butene is great. This one we talked about has 2 stereo centers. Hexa gives me a 6 carbon chain. One of them is at position 2, and one of them is at position 5. At position 2, I've got this stereo center, and it's telling me that my stereo center alkene should be a Z. Is that a Z alkene? It's not. That's an E alkene. Now, I drew this because we were used to drawing bond lines zigzag. But it really, to fix it, I can just erase this and switch one of those groups to be zig-zig. And now I've got a Z alkene at position 2. And then at position 4, I had a methyl, and that methyl group was S. All right, well, here is my 3rd priority is methyl, my 4th priority is hydrogen. This is a shorter carbon chain, so it's going to die out sooner. This is a longer carbon chain. It's going to live longer. So 1, 2, 3. I want it to look S. So I want my hydrogen going back. This will be a wedged group. Does anybody notice a mistake I made in this name? I didn't do this on purpose. If you just saw that structure, how would you name it? Which way would you start numbering? From the right. And so what alkene positions would you have? I didn't do that intentionally. But this is numbered the wrong way. This structure should actually be called SZ3-methyl 1,4-hexadiene. All right, and the last one is 3-bromo 1-methyl cyclopentadiene. You'll notice that cyclopentadiene doesn't tell me the positions of the dienes. Cyclohexene, we needed to say that, but cyclopentadiene, it doesn't matter. There's only one way they can have two alkenes. They'll have one sp3 carbon in between them. Now, I number this as 1, 2, 3, 4, or 1, 2, 3, 4, 1-methyl to 3-bromo. I'm going to redraw that for those of you that can't see the bottom of the board so well. Do we have questions on the nomenclature? Okay. How do you prepare an alkene? Could you guys give me a different word for prepare? Rather than saying, how do you prepare an alkene, you might say, what's a fun chemistry word you can use? What? Synthesize. Synthesis of alkenes, or how to synthesize alkenes. What does synthesize even mean? You guys ever played on a synthesizer? You have?
I mean, I've like messed around with my friends.
I don't know that I've ever played on a synth. I'm not sure why it's called a synth. Because you can make new sounds. Do you guys use synthesis in any other context? You what? Photosynthesis. Oh, I didn't think about that one. Good job. Maybe you might hear someone say like synthesize a solution, synthesize an answer, synthesize a thought process. I don't know. Can you think of anything else? Well, do you understand what we mean it for in this context? Synthesis is the creation of, the preparation of, a way to make. Alkenes are made by elimination reactions. Predominantly. You can also make alkenes by addition reactions. We'll see that later. You can also make alkenes by substitution reactions. You'll see that in OChem 1. But for OChem, you'll see that in OChem 2. For most of OChem 1, we're making alkenes by elimination reactions. One of those elimination reactions involves a halogen and an adjacent hydrogen reacting with a base. This can be referred to as dehydrohalogenation. We oftentimes refer to the carbon with the halogen as the alpha carbon, which means that the carbon adjacent to that is the beta carbon. Can you remind me how we refer to a pi bond in organic chemistry? The property that a pi bond creates in a compound, the characteristic of a compound that a pi bond gives it. a degree of unsaturation. And if that degree of unsaturation comes from alpha and beta, then we can refer to an alkene as alpha beta unsaturated. You agree? If we call one position alpha and the position next to it beta, and then we unsaturate that position, now it's an alpha beta unsaturated group. A similar reaction is when we take alcohols. But alcohols themselves are bases, which means they will not, a hydrogen from a carbon won't be taken by a base if there's a hydrogen on an oxygen. Instead, we use acids with alcohols, and we produce water. Rather than dehydrohalogenation, this is referred to as dehydration. Remove an equivalence of water from the structure. With that in mind, I want to look at these examples and discuss what alkenes can we synthesize. We'll identify the alpha position, and we'll identify as many beta positions as there are so that we can decide where I can remove a hydrogen and the halogen. I should have put an alcohol on here, and I didn't. But we can kind of imagine something similar with alcohols. Can you describe the degree of substitution of my alpha carbon here? Methyl, primary, secondary, tertiary, quaternary. What is the degree of substitution of my alpha carbon? Primary. The carbon with the halogen is attached to one other carbon. What would that one other carbon be? Beta. So how many positions can this alpha carbon remove a hydrogen from in order to make an alkene? 1. Here's a hydrogen that I can remove. Here's the alkene that can be formed. Do we remember the name for this alkene? It's in your notes if you don't remember it off the top of your head. You could name it systematically, which would be two carbons. Oh no, you guys got ran over this week, huh? Come on, name it systematically. What's two carbons? Eth, and suffix for your alkene, ene. We could just call this ethene, but it's often called ethylene for whatever godforsaken reason. It's like the ethyl alkene, of course, which is what ethene would be. Okay, do you guys agree here that the only alkene product that could be formed is ethene? There's nowhere else to take a hydrogen from. There's no other carbons to form a double bond between. What about here? What is the degree of substitution of my alpha carbon? It's now secondary. I'll do this in a different color. This color is stuff. How many beta positions are there? There are 2 beta positions. So how many places could I take a hydrogen from and kick off the halogen to form an alkene? 2. One of them on the left, one of them on the right. Oh, wait, whoa, hey, isn't that a stereoisomer alkene? Would I only be able to form the the E alkene? Or is it possible I could also form the Z alkene? This molecule is able to rotate. If it's able to rotate, that means it might form an alkene from a different conformation, which leads to a different stereoisomer. This alkene, this starting material could synthesize an alkene at two different carbons, and one of those carbons creates a stereocenter out of the alkene, which means we have two possible alkene starting materials. It's not starting materials, I'm sorry, products. All right, let's look at our third one. Degree of substitution, primary, secondary, tertiary, or quaternary at the alpha carbon. Tertiary. That means I should be investigating 3 different places where an alkene can be generated. It doesn't mean that there are actually hydrogens at those positions. So I have to check that there's a hydrogen I can remove. But if there's a hydrogen at each of those positions, there are at least 3 alkenes. And if there are any stereoisomers, potentially more. So let's look first at the hydrogen that could come off of the methyl carbon. This is my alpha, this is my beta. I'm looking to make it alpha beta unsaturated. There's my alkene. Here's my second beta position, the secondary carbon in the ring. Is there a hydrogen there? Yeah, that means that I can do an alkene formation at that position. Here's my alpha, here's my beta, unsaturated. Can you predict the structure of the third alkene? Can you name it? Why don't you turn to your neighbors and see if you're able to predict them? If you can't, just give them a shrug. Is it doubled up? There's nothing different about that than the ones we've done before. Find the lowest locus set. You're working on it? We found that there are 3 positions next to that alpha carbon. And we took hydrogens from 2 of them, so now we're looking to take a hydrogen from the third. You know how to name it, Elise? got it? Okay, let's review. We said this is the alpha carbon. Why? It has the halogen. That means anything connected to alpha is beta. Why? Because that's how the alphabet goes. Alpha, beta, A, B, Aleph, Ba. I don't know any other languages. I think it's the same in Spanish. Anyways, there's a hydrogen here, correct? So we removed one of those hydrogens with the halogen, unsaturated alpha and beta. There's a hydrogen here, correct? So we removed that hydrogen with the halogen and we made alpha beta unsaturated. Is there a hydrogen here? Yeah. So we remove that hydrogen and the halogen and we get alpha beta unsaturated. And what did you end up naming it, Peter? 1,2 what? 1,2-dimethyl cyclohexene. Good. Clear as mud, yeah? These are how we'll synthesize alkenes, predominantly. All right, we've got one last one. Can you solve it? How many alkenes can you predict being made from this this structure here? I'll give you a hint. What is the degree of substitution of the alpha carbon? Secondary, which means that you should have at least 2 possible alkenes, so long as all of those positions have hydrogens on them. Can you predict it? Take a hydrogen from those beta positions and just draw an alkene. And then name it. Of course, what fun would it be if you didn't name it? We've got 2 possible products. The other one is when this beta has its hydrogen. All up. Think about mapping your carbons. Label a carbon however you want. I'm labeling that carbon as alpha. You could label that carbon as triangle, or as star, or as the number 1. And then map that onto your product. Here's alpha. Okay, I want to go, my alphas look a little bit different. I'm going to redraw these a little bit. That's alpha. That's alpha. And here's beta. I've mapped my alpha. Let me map my beta. And I want to draw a double bond between this alpha and this beta. Mapping is not just numbering one structure, it's numbering two structures where you're keeping positions the same. Numbering your carbons is good. Mapping your carbons from starting material to product is numbering the carbons in a specific way and then numbering them in that same way again in the product. I want to draw a double bond, alpha, beta, unsaturated. Here's alpha, here's my other beta, alpha, beta, unsaturated. So you should have gotten 1,5-dimethyl cyclopentene and 3,4-dimethyl cyclopentene. Those are our two products. All right, now the last one. How many elimination products can be made from 1-bromo, 2,2-dimethyl propane? 1. Kiara, are you predicting this? Any issues? Did I steal a hydrogen to make that alpha beta unsaturated? What? How do you mean no? I didn't steal a hydrogen? Huh? For the wrong direction. Well, there's no other carbon. Here's alpha carbon. Here's alpha. Here's beta carbon. Here's beta. I made alpha beta unsaturated. Did I steal a hydrogen from beta? Does beta have a hydrogen? I didn't steal a hydrogen, but I still made a bond. So what's upsetting about that structure? Too many bonds. Breaks the octet rule. I've got 5 bonds going to my carbon. And here's the deal. Chemistry has all sorts of wacky structures. 5 things going to phosphorus, 6 things going to sulfur. And so when you draw something strange like this, it doesn't always register as wrong. But carbon cannot make more than 4 bonds. So when you've got 5 bonds going to a central carbon, should be a big red flag. Something's wrong about this structure. This structure doesn't exist because this can form no alkene. No alkene product formed. Is that fair?
Those are not an alpha carbon?
Sure, there's an alpha carbon, but there's no beta hydrogen. Yeah, we said that we can call this dehydrohalogenation. I need to remove a hydrogen from a beta position. If there's no hydrogen at a beta position, nothing to remove. If no beta hydrogen exists, no elimination occurs. What questions can I clarify about this process?
Wait, how do you know? I'm still pretty confused. How do you know how to pick out which carbon is the alpha carbon?
Yeah, anybody want to take this? That's it. Or the alcohol.
Okay. Okay, I see. Okay.
That's all. The alpha carbon is the one with some functionality on it. The halogen or the alcohol. And the beta carbon? How do you identify a beta carbon? It's connected to the alpha carbon, alphabet. Can anybody answer why only one of these reactions gave me a mixture of stereoisomer alkenes? The blue reaction, I got both trans-2-butene and cis-2-butene, but none of the other ones gave me a trans and cis isomer. The rings are under 8, so I'm not able to form trans and cis isomers. And most of these were rings. The only other linear one wasn't a stereocenter alkene. True, and one did nothing. So rings will never have trans cis unless they're above 8 members. So we're not going to deal with them very much this semester. Only one of them actually created a stereocenter alkene that that could have been in 2 different configurations. All right, good work. On to the next. We're going to be using this resonance template to explain a little bit about alkene reactivity. Alkenes have preferred regioreactivity. And we can demonstrate their preferred regiochemistry by looking at resonance forms. In general, I ask my students to never double up on showing electron arrows on a structure. But for this example, we're going to. We're going to show this alkene, 2-methylpropene, forming 2 different resonance forms. In one of them, we'll take the pi bond and isolate it on the primary carbon, which means the tertiary carbon has lost those pi electrons. I get this localization of charge, negative and positive. And we're going to compare that to taking the pi electrons and putting them on the tertiary carbon. What is the difference between these 2 resonance forms on the left and right? Actually, I'll tell you something they have in common. Neither of them are as stable as the structure in the middle. You agree? Why? This was on your midterm. We haven't minimized the charge. These 2 resonance forms that we've just created maximize charge. So they are not a preferred resonance form, but they will explain the regioreactivity for us. These 2 resonance forms are not equally stable. One of them is better stabilized, and one of them is more destabilized. Let's think about the electrons. This is a lone pair of electrons, and it's sitting on a carbon that has 2 hydrogen groups on it, and this big carbon group. You guys might remember from Gen Chem that lone pairs of electrons repel other electron pairs the most strongly, the strongest. Which means lone pair to lone pair repulsion is very strong. Lone pair to bonding pair is fairly strong. Bonding pair to bonding pair is the weakest repulsion. So I want my lone pair of electrons to be as far away from other electrons as possible, because that lone pair of electrons will be repelling other electrons a lot. There's not a lot of electron pairs, there's not a lot of bonding electrons near this lone pair. Let's consider the other structure. I've got a lone pair, and then I've got these 3 big carbon groups, CH3, CH3, CH2. there's a lot of electron density sitting around that lone pair. This lone pair has to push away a hydrogen, another hydrogen, and an alkyl group. This lone pair has to push away 3 big, bulky alkyl groups. Which lone pair is more destabilized? The one on the right. Which lone pair is the least destabilized? The one on the left. This puts up the smallest fight, so it's more stable, less reactive. This puts up a big fight. Now I want to talk about the positive charge. True or false, positive charge, a positive charge is an attraction for electrons. Electrons are attracted towards regions of positive charge. Yeah, that's electromagnetism. Positive and negative charges attract one another. And if a positive charge had a big barrier of negative charges surrounding it, then it would be more stable. It'd be as if it can borrow some of that electron density from more electrons around it to help quiet down its positive charge character. I call it moral support. Which of these positive charges gets the most moral support?
Probably the centralized one.
On the tertiary carbon? If we actually look at some of the regions in here, I'm going to explicitly show one of these CH bonds, one of these CH bonds, and I've already got this CH bond here. Over here, I'm just going to clarify a little bit better these CH bonds. This positive charge is surrounded by electron density. It's got all of these bonds, all of these electrons that can actually hover over the positive charge, stabilize it, make it less reactive, moral support. Whereas this positive charge, well, it's got 2 itty-bitty little hydrogens, and then it's got 1 alkyl group that it can borrow some electron support from. This positive charge is more stable. This positive charge is less supported. So we've said that this structure on the right is an unstable positive charge and an unstable negative charge. And this structure on the left is a less unstable negative charge and a more stabilized, a more supported positive charge. So which of these resonance forms is preferred? Which of these resonance forms is more stable? Structure on the left. Here's the impact it has on the regioreactivity. Less substituted carbons have partial negative character. More substituted carbons have partial positive character. Early on, we learned about electron pushing, and I gave you guys this tip. When a bond breaks, it goes towards the more negative atom. Let me actually explain. This looks a little confusing. Here's our 2-methylpropene, and I'm showing partial positive on the tertiary carbon, partial negative on the primary carbon. When a bond breaks, it goes with the more negative atom. Which means in this case, if these electrons ever leave to go attack an electrophile, it is the less substituted carbon that bonds to the electrophile and the more substituted carbon that loses the electrons. Hey, what a good spot to put a positive charge. That positive charge is surrounded by electron density, moral support that is stabilizing the positive charge. All right, now there is a technical term. It's not really called moral support. This is called hyperconjugation. And try as I might to explain hyperconjugation in the past, it never seems to make a difference on explaining why carbocations are stable the way they are. Students just don't really get it. Hyperconjugation is the moral support of having regions with a ton of electrons nearby to support electron density. It's technically something to do with the overlap of molecular orbitals with empty p orbitals. But we'll leave that for a higher level chemistry class. All right, let's take a break. 5 minutes. Let's come back at 6:10. We'll talk a little bit more about carbocations, the way that alkenes react, and we should have some time to even start in our alkene addition reactions today. I encourage you to get up, move around, and get your blood flowing so the second half feels more alive. More alive than dead.
Yeah, I'm gonna go.
That's real. Mm-hmm. That's hyperconjugation, by the way, in case you were really itching to know. That's moral support. Empty positive charge steals electrons from a bond. The more bonds nearby, the more support. Hey.
You were saying when the bond breaks, the electrons from the bond go to the more partial negative side.
Yeah, well, that's always, not just alkenes. We said that all the way back in Unit 1.
With the characters, though. I don't know, that's confusing me that it has a symbol. So.
Partial positive, partial negative. We've used that. We use that when we talk about bond polarity. That delta.
Yeah.
Yeah, it can look a little bit like an S, but it's got a touch. It should actually look like a funky little D, because it does come from delta. It's delta positive, delta negative. That's bond polarity. Why is a carbon-carbon bond polar? That's carbon-carbon, isn't it? Why am I drawing a carbon-carbon bond polar? What do we base polarity on? In this case, yeah, we can determine polarity by substitution of the carbon. That's true. But all the way through Gen Chem, differences in electronegativity. What's the difference in electronegativity between carbon and carbon? Yeah, there's no difference. So then why am I saying that there's a difference in electronegativity? Why am I saying there's bond polarity? I'm not saying there's a difference in electronegativity. Why am I saying there's bond polarity? Because of the resonance. The resonance shows that one carbon is actually more negative and the other carbon is more positive. And it explains how they react. Because I made a mistake. Oh, shoot. Thanks for noticing that, Natalie. That is. No, it's the same structure. And over there, I said that it was partial negative on the less substituted. I just messed up. Let's review what we just discussed. If I look at an alkene that is not equally substituted, this would be an unsymmetric alkene. I can predict regioreactivity, a partial negative and a partial positive. Typically, we're not allowed to assign partial charges unless there's a difference in electronegativity. But here, we've seen resonance forms, where a more substituted carbon steals electrons from neighboring bonds. The more neighboring bonds, the more substituted, the more it can steal electrons, the more stable it actually becomes. So this has regioreactivity. What about this? Can you label a partial negative and a partial positive on this alkene? Partial negative where? On the terminal carbon, the less substituted. Partial positive on the more substituted. Again, that is saying that if these electrons are to react, they will be lost by the more substituted carbon because it's more stable, holding a positive charge, and they will not be lost by the less substituted carbon because that's not as stable. It doesn't form. I want to remind you that we've actually already seen this. Might just take me a while to find it. Organic reactions. When we were looking at mechanisms for the first time, alkene, more substituted carbon, less substituted carbon, 2 possible intermediates. Which one formed? Why? Well, we know it's formed because of the product, but why does this one form and not this? Is that what you're trying to get at?
Yeah,
Moral support.
I'm tired, I'm sorry.
Hyperconjugation. This is a more substituted cation, so it's more stable. A less substituted cation doesn't form. What about this alkene? Does this alkene have regioreactivity? Can I label a partial positive and a partial negative on this alkene? Which carbon is more substituted? Why? It's in the middle, so it's bonded to more carbons? It's not. Those 2 carbons are equally substituted. That means that I have an equal chance of either carbon reacting and I could get 2 intermediates. I'm not really showing the fact that one of these carbons will be bonding to a new electrophile. Like I didn't show that here either. But we're saying if these electrons are to be lost in a reaction to an electrophile, okay, and equal actually doesn't mean 50-50. But this is like 95, 5%, and this is like 60-40. Not your job to predict which, just to be able to say both are very likely. No regio difference, so there's no regio preference. They're equally substituted, so their charges are equally likely to occur. And this gets us into the stability of carbocations. This word always gets mistaken, so even those of us online, I'd like you to repeat this after me. This is not carbocation, like vacation. This is carbocation, like a positive ion. So after me, carbocation. Great job. Carbocations come in a few different flavors. And here is actually a energy diagram that we can use to depict a little bit of this. On the low end, the least stable we have our methyl carbocations. That's a CH3+. Methyl carbocations experience 0 hyperconjugation. They have nothing to steal electrons from to get support on their positive charge. Then we have primary carbocations, for instance, like this ethyl carbocation. This is a bit confusing that it's just a line, so we can sketch in CH3, CH2. The primary carbocation can steal electron density from its one neighboring alkyl group. Then secondary carbocations and tertiary carbocations. But that's not the end of our chart. Because cations stabilize even better if that charge is not localized. if that charge can delocalize, then the charge at any one position is smaller. So resonance stabilizes charges. That means allylic carbocations. And here's the slightly confusing thing. Substitution stability starts over after resonance is included. Primary allylic is more stable than tertiary with no resonance. Tertiary gets a lot of moral support, great. Primary, it's literally split in half. That's a plus 1/2 charge. This is a plus 1/2 charge because of resonance. What would be more stable than resonance at an allylic position? You want to guess, Yoon? We look at resonance at a benzylic position. Can anybody remember what benzylic is? That's adjacent to the benzene ring. So you go methyl, primary, secondary, tertiary, methyl allylic, secondary allylic, tertiary allylic, primary benzylic, secondary benzylic, tertiary benzylic. Within that allylic and benzylic groups, the substitution trends continue, but the resonance greatly stabilizes the positive charge compared to no resonance at all. We're going to be dealing mostly with the left-hand side. We'll look at allylic and benzylic later in the semester and more in OChem 2. We're going to be dealing mostly with this substitution on the left. This goes back to the same idea, which is if two carbocations are capable of forming, the more stable carbocation will form. If I have, we can actually look at this structure here. If I have the potential of forming a tertiary carbocation or a primary carbocation, the primary carbocation sits higher in energy and is more challenging to form. If I have enough energy to form a primary carbocation, I already had enough energy to form the tertiary carbocation instead. If you have enough energy to get up here, you won't. Does that make sense? I think the other day I mentioned that reaction coordinate diagrams don't need to be two-dimensional, but reaction coordinate diagrams can actually be three-dimensional. They can show that a molecule has an energy field that it can move across, which means a lot of different things are capable of happening depending on how that molecule experiences changes in energy. I'm going to try to demonstrate a three-dimensional reaction coordinate diagram with this to talk about this next feature. Carbocation rearrangements. If a carbocation forms adjacent to a more substituted position, then groups can actually shift their electrons around to create a more stable carbocation. That's a lot of words. So let's give an example. If I took this 2-methylpropene and I reacted it with this hydrogen, and if I bonded the hydrogen to the more substituted carbon and I formed a less stable carbocation, the hydrogen can actually shift with its electrons to leave a positive charge in its wake. This hydrogen takes its electrons to the adjacent carbon, leaves a positive charge in its wake. That only occurs if it creates a more stable carbocation. So here's what we'll say. Hydrides, you guys know the suffix IDE indicates a negative charge. So hydride is indicating H minus. That's hydrogen with a lone pair, or hydrogen with a bonding pair. Hydride and alkyl groups, we're often going to look at methyl, CH3 minus. We're going to look at methyl shifts. They will shift one position, only one position, if and only if a more stable carbocation forms. Would you agree that the arrow pushing I have in red, in green, up on top, shows the formation of this blue line to the primary carbocation, then the transformation of this primary carbocation to this tertiary carbocation directly? This image was designed to be an overlay of the energy of two possible scenarios. But I want you to imagine for an instance that it's actually three-dimensional and the blue is sitting behind the red. What I'm showing in this arrow pushing is the blue moving through a transition state to the pink. It goes from this energy, it has to overcome a small energy barrier, and at the end, it's now at a lower energy. It's more stable. And I fear that that was not a great demonstration. I want this to appear as if it's behind the pink. Does it look, do you get it? Sorry, I've not done this before. You can kind of see how this carbocation has to overcome a small energy barrier, and then it can actually get to this position. The only reason it will shift is if it results in a lower energy carbocation, a more stable carbocation. Primary would shift to secondary, primary would shift to tertiary, primary would shift to allylic, primary would shift to benzylic. If there's any change towards more stable, a shift will occur. Here's an example of a hydride shift. That's what we call it. hydride shift. Okay, so earlier we were looking at a structure, and we said that there were two possible alkenes that could form. I'm not sure if I want to get rid of this yet, so I want to keep it for right now. We said that this structure could form two possible alkenes. An alkene here and an alkene here. I want to demonstrate how a carbocation rearrangement actually allows for the production of a third alkene. If this structure, and this is actually what's at the bottom of this page, it shows it to you here. If this structure first loses its OTS group, that is, the O bond breaks towards the oxygen, the CO bond breaks towards the oxygen. What is the substitution of my carbocation? Primary, or methyl, primary, secondary, or tertiary? The carbocation carbon is bonded to two other carbons, so it's a secondary carbocation. What's adjacent to it? What has bonds right next to it that could scoot their bonds over? Here's a secondary carbon, and here's a tertiary carbon. So the question is, if the secondary carbon scooted over one of its hydrogens, the positive charge would be left behind on this carbon. Would that make it more stable? No. Secondary to secondary is equally stable. What if the tertiary carbon scooted over one of its hydrogens, its only hydrogen, and left the positive charge on the tertiary carbon? Would that be more stable? Yes. Tertiary carbocations are more stable than secondary. So if it can happen, it will happen. In fact, it happens this quick. Did you catch it? You're right. I actually was going to snap, and then I was like, that'll take too long. Here's the arrow pushing. H and its electrons shift over. Leaving behind now a tertiary carbocation. So earlier we said that there were two products of alkenes that could form from that structure. Because of this carbocation rearrangement, there's now a potential for a third. This is a new alpha position, and this is a new beta position. So we now have this potential for a new alpha-beta unsaturated product if and only if the alkene forms with a carbocation intermediate. That's why I put it there. So I wanted you guys to look at this. We know we could put an alkene here. We know we can put an alkene here. How would it be possible to put an alkene 2 carbons away from the alpha carbon? if and only if a structural rearrangement occurs. So I want to transition this train of thought a little bit. These are now the 3 possible alkenes from that starting material. How would you know which, if any, you formed? Could you use IR to tell you which of these alkenes you've made? You know, actually, this tetra substituted alkene, it doesn't have any sp2ch, and its CC double bond would be very weak, whereas these would have CC double bond and sp2ch. But it wouldn't be easy to use IR to tell them apart. Would NMR be useful? Certainly. No vanillic hydrogens, 1 vanillic hydrogen, 2 vanillic hydrogens. NMR would be super handy for telling which of these alkenes you isolated. And that's exactly how we can prove that structural rearrangements like this occur. You can believe me that all of this happens, or you can go home and be like, that was so BS. No way that atoms do that. The bonds don't shift. It's all a lie. But then we can go down and we can take the NMR of a starting material, and we can take the NMR of the products, and we can prove that there must have been this rearrangement of atoms in order to get that specific product. This is another reason why I teach you spectroscopy early on, so that you can actually prove spectroscopically that these reactions happen the way that we're saying they do. Okay, let's look at a hydride. This was a hydride shift. Let's look at a methyl shift. This time, I want to look a little bit differently. This was in the direction of forming an alkene. Let's look in the direction of reacting with an alkene. Can I predict regioreactivity at this alkene? Can I predict partial charges on this alkene? Think back to this resonance form. How did we say that these resonance forms informed about partial charge? Where is the partial negative on this atom? More substituted on this atom. Where is the partial negative charge on this molecule? The more substituted carbon or the less substituted carbon? On the less. Partial negative on the less substituted. Partial positive on the more substituted. If this alkene is in the presence of an acid, it's the more negative carbon that uses the electrons. It's the more positive that loses the electrons. I go from having a CH2 group to a CH3, and now I have a secondary carbocation. Next to it is a primary carbocation. Secondary carbocation. If I take a hydrogen from the primary carbon and I shift it over and I leave a primary carbocation, is that more stable than what I currently have? No, so it won't happen. Is there a hydrogen on the quaternary carbon to the left? No, so I can't do a hydride shift. Hydride shifts, if possible, are easier. All you have to move is a little proton with electrons. If there's no hydrogen, then you have to think about moving bigger groups. What if I took a methyl group off of this quaternary carbon and I shifted it with its electrons? Earlier I said that's going to be this methyl shift. CH3 minus. First of all, would I still have a quaternary carbon after that methyl shifts? It's losing a carbon. And it would have a positive charge left on it in the wake of the methyl group moving. So what would it be? A tertiary carbocation. So methyl group shifts over, that CH3 and the bonding electrons moving. CH3 bonds to the secondary carbon. Are you okay with the fact that the secondary carbon just became a tertiary carbon? You should be. It just took on a carbon group. And the quaternary carbon just lost a group. It has a positive charge in its wake. Is a secondary carbocation more stable than the tertiary? Tertiary is more stable, so this is favorable. That's why this occurs. It's this. It's my ugly little drawing. See if I can line it up again. It's shifting from a less stable to a more stable carbocation. It has to move a big old group to do that, but it will do that. Methyl groups are the only shifts that we'll really look at in our class, but all sorts of alkyl shifts happen. In fact, ring expansions are very common. Ring expansion is where the alkyl group is, oh, sorry, this is all blurry. The alkyl group is in a ring, and so it moves a bond over, and that results in an even larger ring forming. We're not going to look at it either, but you can do multiple carbocation rearrangements sequentially. So sometimes a ring expansion results in a less stable carbocation adjacent to a more substituted position, and then it's followed by a hydride shift. What you can't do is shift by more than one position. So two things I want to point out. Some students will say something like, let's take this hydrogen and shift it all the way across. It has to be a shift on an adjacent carbon. Another very common error that I see, students trying to show the carbocation is rearranging, will show something to this effect. They'll show the positive charge moving to a different carbon. What do we call this arrow again? Its full legal name is electron arrow. What electrons are in the positive charge? None. The whole point is that the positive charge is a lack of electrons. The carbocation is rearranging by nature of a hydride shifting or a methyl group shifting, leaving a new carbocation in their wake. We're going to be looking at a lot of reactions that have carbocations as intermediates. And every time we form a carbocation, we have to look at it and analyze. Could this be more stable on an adjacent carbon? Is there a hydride shift or methyl shift that will cause this to be more stable? When you get into Alkene 2, you'll focus a little bit more on benzylic positions. Could I shift to a benzylic position to see this become even more stable? Oh, it's so much fun, guys. I'm like exhausting myself just telling you. What questions do you have on this? I have this new worksheet for you guys. There is no way that we will get through all of it, but I do want to make some headway on what we're getting into next week. So I'm going to hand these out, and I think what we're going to do is we're going to write down the names of these 11 reactions that we're going to learn. Next week, what we'll do is we will fill in the chemical reagents that are needed. We'll look at the problem solving for them. And we're going to learn their mechanisms next week as well. Listen, they teach me in teacher school that the least productive time in a class period is the last 10 minutes. But I just can't send you home. I mean, you guys are adults. You know you can walk out anytime you want to. Okay, full transparency, this is my first time teaching it this way. I almost always show my students that there's a graphic like this that shows how all of our reactions for alkene addition reactions can be shown from one starting material and then highlighting all of the different products that you can make. But what I typically do in class is I go one by one through the reaction and I show examples. I'm deciding not to do that anymore. We're going to do it this way. We're going to fill out this reaction map. We're going to show how one starting material turns into all of these different reactions. And then there were 3 reactions that I wanted on a different starting material. So reaction number 1, this is not in any particular order other than the fact that I like to go this way. Reaction number 1 is the HX addition reaction. X2 is the, number 2 is the X2 addition reaction. This is also called hydrohalogenation, HX, and halogenation, X2. The reaction with halogenation changes if there's a different solvent. So X2 with alcohol and X2 with water, which is the halo ether and halohydrin addition reactions. Is it too late? I think actually we should switch to talk about active. Will, those active problems that you were mentioning last?
So in the matter of 20 minutes, it went from not understanding how to do them at all to completing them on the first try.
Do you think that it would still be worthwhile to talk about it together?
Yeah, no, I think that would be great to talk about.
Maybe this would be a better way to end the class, since it's a little bit more on what
Saying
we're
that
doing.
You explained it very well today, so like I got it.
Today's class, you think made it understandable as well? Well, let's do it anyways. I'm not a big fan of the structures to begin with. I don't like that they show skeletal structures with no arrows. Am I in the wrong?
It's 7.
I'm in Unit 7, Section 7. What numbers are they?
For me, it was
Oh, it's some of the first ones?
yeah.
Oh. Okay. Are you guys okay with talking about these problems instead? Probably better.
I just didn't really understand the wording until today.
The wording is weird, and today's activity was meant to try and highlight this, but... All right, this question says, this carbocation is an intermediate in a reaction with an alkene, 2 different alkenes, and HCl. Identify the 2 alkenes that would selectively generate this cation. You're given a 3-dimensional model, but you can't move it. So there's some tricky parts here, which is that this carbon has no hydrogen on it. If it's bonded to 3 things with no hydrogen, that means it has a positive charge. So we're looking at this structure. A cyclopentane ring with a methyl group coming off and a positive charge. And the question is, what 2 alkenes will react with acid to selectively form this carbocation? That's fair. Actually, that big fat arrow means what did it come from? It's pointing to the starting material. This carbon of the carbocation, that should be in the alkene. So then how many possibilities are there for other carbons to be in the alkene? 1, the methyl group. Those could be the 2 carbons of the alkene. But then what about these 2 positions of the ring? Shouldn't there be 3 possibilities? They're identical positions in this symmetric molecule. So these 2 positions could be an alkene. These 2 positions could be an alkene. And this reaction they're talking about, electrophilic addition with HCl, that's the HX addition that we're going to talk about next week. This one is very similar. It says the alkyl bromide below is the product of electrophilic addition with HBr and 3 different alkenes. So we need to figure out, again, the 3 different alkenes. Once again, it's really hard to interpret those 3-dimensional models. But we're looking at a cyclohexane ring, an ethyl chain with a bromine, and then a methyl chain 2 carbons away. So this is kind of backwards of what we were saying in class. In class we said, what alkenes could you make from this? And this is saying, what alkenes can be used to make this? Those are really the same question, just directing your attention in different ways. Here's your alpha carbon. How many beta carbons do you have? 3. A beta carbon here, here, and here. Well, didn't we just say that the 2 carbons in the ring are equal to each other? Aren't these 2 positions in the ring equal? Why not? That methyl group means there's no symmetry here. That's a different alkene than this. Okay, those were probably the 2 hardest questions on the section 7 homework. I wanted to talk about those, and that ate up the rest of our time. That's way better than just giving the names of the reactions. All right, next week we're learning those 13 alkene addition reactions. We're learning reagents, functional groups they form, and then we're also going to be learning the mechanisms, the arrow pushing and the intermediates for 4 of them. So feel free to get a head start on the reading, the active, and that worksheet if you want to. And we will pick up there on Monday. Have a good weekend, everybody.
Is this
Section 8 material on Monday.